Hi everybody, I hope you are doing well, and these are your notes for Unit 7, Exponents and Powers, and we're going to be doing 7.1 and 7.2. We're dealing with, for 7.1, prime factors and exponents, and the following part is how can we express the value of an expression in exponential form. This is where you're going to go ahead and put in what your claim is or what your support and your question. And remember, this is not something that you're getting graded on. This is just, hey, you know what, based on this question, what can I take away or what can I get from here? Look at the context clues that are in the question. And then once you've done that, you can move on. So either you can pause here and go ahead and fill this out, or you can move on. It's up to you. All right, how can a value be expressed as a power? Well, what is a power? The term 2 to the 7 is called a power if a number is an exponential form. So the exponent represents how many times the base is to be used as a factor. So this whole thing is called a power. The 2 itself is called a base, and the 7 is called an exponent. So how is a power evaluated? A power is evaluated by finding the value of the expression. So substituting the values of the variables and using the order of operations of values evaluates the expression. This one here, for example, is not something where we're going to substitute in for a variable, because this is not a variable, a problem with a variable in it. This is just to show you what you're doing. So literally, if I was to expand this out, it's the same thing as 2 being multiplied 7 times. 1, 2, 3, 4, 5, 6, 7. Okay, just making sure. So then you would multiply 2 times 2 times 2 times 2 times 2 times 2 times 2. And you'd get your answer. And this is the way we rewrite it in expanded form. All right, so how can a value be expressed in its most prime form? Well, what is prime factorization? Prime factorization is a prime or prime number. I guess that's something that we need to talk about first. A prime number is a counting number that only has 2 factors, itself and 1. Counting numbers which have more than 2 factors, such as 6, whose factors are 1, 2, 3, and 6. So remember factors. Let's talk about what a factor is, because the word factor keeps coming out here, keeps coming up in here, and it might not be something that you remember, but a factor are, hey, what numbers multiply to give you the number? So when we're talking about 2 factors that give you 6, such as 6, their factors are 1, 2, 3, and 6. Because 1 times 6 is 6 and 2 times 3 is 6. Those are all the values that can somehow be multiplied by one other number to make up the number. So counting numbers that have more than 2 factors are called composite numbers. So these are actually both vocabulary words. Prime number, composite number. When a composite number is written as a product of all of its prime factors, we have the prime factorization of the number. So it might be a little bit wordy, but I'm going to go ahead and explain that to you. So we're going to use exponents to write the prime factorization of 28. So 28 gets prime factorized, and you know, I like the way that they set it up here, but I have another way that I like to do prime factorization, and I take my number, which is 28, and when we're thinking about prime numbers, the numbers that you typically think about with primes are going to be, and I'm going to write those up here, some prime numbers, 1, 2, 3, 5, 7, 11. There's a lot more, but it's literally numbers that are divisible by 1 and itself. So 1 is only 1 times 1, 2 is only 2 times 1, 3 is only 3 times 1, 5 is only 5 times 1. You can't use any other whole numbers to multiply together to give you that number. So when I'm looking to prime factorize a number, I look at what I'm dealing with and I go, okay, I have the value of 28. I know 1 can go in 28. You typically don't use 1 as the prime factor if it's, unless it's a negative, which we'll get into later. I do know that 2 goes into 28. So when I write this, I write it so that I have 2, and I know 2 times 14 gives me 28. So this times this will give me 28. I put 14 up here because I know 14 cannot be is not a prime factor. I know there are 2 numbers that multiply to give me 14, and then I think about the 2 numbers that multiply to give me 14, and right away I come up with 2 times 7. And I put those both down there because these are both prime factors. 2 is only divisible by 1 in itself, and 7 is only divisible by 1 in itself. So I know 2 times 2 is 4 times 7 is 28. This whole thing multiplied together gives me this. At this point, even though I wrote that 14, I'm going to ignore it. I don't need anything to do with it. I prime factorized 28. I know that the multiples are 2, 2, and 7. A lot of times when students are learning this for the first time, they're given the value of 28, and I see they did 4 and 7 here, but let's say I started with 2 and 14, and I know 14 can be brought down again by 2 and 7, and you ignore these numbers because you've already factored them to be 2, 2, and 7. That's called like a factor tree. I have a name for this one here. I call it a factor hedge. You know, a hedge like a bush that goes side by side. I feel like it's much neater for me to see it this way. You can go either way, whichever you want. So now what we're going to do is we're going to use exponents to write the prime factorization of 28. So I know that 28 is 2 times 7. And in order for me to write that with exponents is I know that I have 2 being multiplied by twice. So 2 to the second power is the same thing as 2 times 2. And then once I do 2 to the second power, I multiply it by 7. So 28 is equal to 2 to the second power times 7. This is the prime factorization of 28. I'm actually going to just do one more for the sake of the problem. Let's go ahead and do 24. I'm going to think of a prime number. I know 3 is a prime, and 3 times 8 gives me 24. I put 8 up top because I know 8 is not a prime. Then I think of 2 numbers that multiply by 8, one being a prime. 2 times 4. 4 is not a prime, so I put it up here. 2 numbers that multiply to give me 4 are 2 times 2. So the way that I literally can read this is 2 times 2 is 4, times 2 is 8, times 3 is 24. However, I'm going to ignore the 8 and the 4 because I've already prime factorized this. And now I want to rewrite this in where the exponents, we're going to rewrite 24 as factorization, a prime factorization using exponents. I have 3's not repeating. Oops. So because 3 is not repeating, I'm only going to have 3 by itself. However, I have 2 multiplying 1, 2, 3 times. So that would be 2 to the third power times 3. Now, once again, I can go ahead and do this as a tree, a tree. 24 is the same thing as 3 times 8. 8 is the same thing as 2 times 4. And 4 is the same thing as 2 times 2. And like I said before, you ignore these ones and you only look at what the factors are. So you have 2 ways you can do this. You can do the factor hedge like I do, or you can do the factor tree, whatever you prefer. All right, so it says you try. So you try writing the prime factorization of each number. Use exponents if possible. If the number is prime, write prime. So I'm going to do a couple of these with you. You can go ahead and do some on your own. I'm going to go ahead with 32 first, and because I told you I like to do the factor hedge, I literally can do this side by side. So thinking about 32, I know 32 is divisible by 2, which is a prime. 2 times 16 gives me 32. 16 went up top because I know it's not a prime. And then I know the next one would be 2 times 8. 8 goes up top, not a prime. 2 times 4 gives me 8, goes up top, not a prime. And 2 times 2. All of those are prime. So double checking, working backwards, 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32. So to write this in, write the prime factorization and use exponents if possible, all I have to do is count. I have 1 being multiplied 1, 2, 3, 4, 5 times. So this is 2 to the 5th power. 2 to the 5th power is my answer for this one. 31. 31, not divisible by 2, not divisible by 3, not divisible by 5. I'm going to go ahead and take a shot in the dark, and I'm going to say 31 is only divisible by 1 and itself, so therefore 31 is prime. Next, I have 49. That is one of the easiest prime factorizations because I know 49 is the same thing as 7 times 7, which would be 7 to the 2nd power. And this is my answer for this one. So I got the answers here. You know what, I'll do one more. Let me do 40. And that's the same thing as 2 times 20, 20 not being a prime, 2 times 10 not being a prime, and 2 times 5. Well, let's go back and double check. 5 times 2 is 10, times 2 is 20, times 2 is 40. So I have 2 being multiplied 3 times, then by 5. And super easy, write each expression using exponents. 6 being multiplied 3 times, 6 to the 3rd power. I think you guys could do the rest on your own. You definitely have the ability. All right, so now we're going to go ahead and prime factorize for algebraic terms. And this is going to be, might seem a little bit more complicated, but it shouldn't be. If we can go ahead and factor a value or a number, we should be able to factor a variable with no issues, no problem at all. So the prime factorization of a negative integer includes a -1 as a factor. Let me explain this one. So we have the following expression, -8x squared y to the 3rd. So because this value, because we have the -8 in front, we cannot say what number or what value is negative within here when multiplying this as a being prime factorized. So when we have a negative in front of the value, we have to factor out a -1. -1 must come out as a factor. So what that means is I have -8 here, and I must factor out -1 because -1 times +8 is -8. Well, now I want to prime factorize the exponent. So what I do is I see, oh, you know what? I have 2 x's being multiplied, so therefore it's x being multiplied by another x. Then it's being multiplied by y to the 3rd, which is the same thing as y times y times y. However, that is not completely prime factorized because I know I have this 8 here, which is not a prime number. So thinking about what I've done before and I have my factor hedge, I know 8 is the same thing as 2 times 4. 4 is up top because it's not a prime, which is 2 times 2. Double checking what I have here, 2 times 2 is 4, times 2 is 8. Remember, we ignore the 4. All we care about is that the 2's are being multiplied 3 times. So using the prime factorization of -8, we got the following right here. -1 times 2 times 2 times 2 times 2. All of those, because remember the -1's already on the outside. The prime factorization for this whole expression is the same thing as -1 times 2 times 2 times 2 times x times x times y times y times y. Don't worry, I wouldn't leave you not being able to have a couple of examples in. I do know it says you try, but let's be honest, I like doing these with you guys too. Remember, if there's a negative, we factor out the -1. -1 times 11. Guess what? 11's prime. 11 is only divisible by 1 and itself. So therefore 11 is factorized, and then I have m to the second power, which is the same thing as m times m. That one's done. We're easy. We're good to go. Next, we have 21, AB. 21 is divisible by 3. 3 times 7. Both of those are prime numbers. 3 is only divisible by 1 in itself, and 7 is only divisible by 1 in itself. And then 3 times 7 times A times B. Super easy. Super, super easy. All right, 45. I know that 45 is divisible by 5. I'm going to use 5 right away because 5 I know is a prime number, and 5 is pretty simple, pretty straightforward. And I'm going to go ahead and put 5. But 5 is a divisible, but it's 5 times 9, and 9 is not a prime. I know 9 is 3 times 3. And then I have J times K. I'm going to go ahead and leave the last one for you to attempt on your own. All right, let's look at this. Evaluate the following expressions if x is equal to -2, y is equal to 3, and z is equal to -1. So literally that means that wherever I have x, I'm plugging in a -2. Wherever I have y, I'm plugging in a +3. And wherever I have z, I'm plugging in a -1. And when I plug in using parentheses. It's the best thing to do. Stick with that. Especially if you have a negative. You want to make sure that you're doing the right thing. So this is -2 to the second power, y, which is 3, times z, which is -1, plus y, which is 3 to the third power. So this right here, and this is where I will see a confusion, I have students that forget that this is a negative. That means I have -2 being multiplied by itself twice. So off to the side here, -2 to the second power is the same thing as writing -2 times -2, which would give me +4. So now I have 4 times 3 times -1 plus this here, 3 to the third power, is the same thing as 3 times 3 times 3. 3 times 3 is 9, times 3 more is 27, so I have 27. And now I just have to multiply these three numbers. 4 times 3 is 12, times -1 is -12, plus 27. -12 plus 27 is the same thing as 27 minus 12. So the answer for this one would be 15. All right, let's do the next one. If 3, -1 to the second power, times y, which is 3, times z, which is -1, plus -2 to the third power. All right, this first one here is -1 to the second power, which is the same thing as -1 times -1, so that's just 1. So I have 3 times 1 times 3 times -1, plus my next one I have is -2 to the third power. -2 being multiplied by 3 times. Negative times a negative is a positive, but times another negative would be a negative. So I have that value is going to be plus -8. All right, 3, okay, looking at this, 3 times 1 is 3, times 3 is 9, times -1 is -9, plus -8. I'm adding two negatives, so I'm going to get a bigger negative. -9 plus -8 is -17. I might need to zoom in on this one here. I have x to the second power. Remember, x is -2 times y to the second power. Y is 3 to the second power minus 2 times -2. All right. I have, my first one was negative 2 to the second power, which is the same thing as negative 2 times negative 2, which is 4. So I have in parentheses 4 times 3 to the second power is 9, and then negative times a negative is a positive. So I'm going to go over here. 9 times 4 is 36, plus 4 more, which is equal to 40.